Hi, I'm Nick Nee, Product Manager of SDSoC Development Environment. In the previous video called Developing a Full System in C++ without writing a single line of hardware code, I showed you how easily you can accelerate an OpenCV application using hardware-optimized libraries. However, almost in every case, a user needs to implement custom algorithms to differentiate against the competition. Similar to algorithm acceleration techniques on different architectures such as DSPs, GPUs, FPGAs also require you to optimize your algorithm to efficiently run as a custom circuit. The good news is that out of hundreds of techniques that exist for Vivado high-level synthesis optimization, you only need to understand a few techniques to get your image processing functions to run in real time. In this video, I will show you a typical user flow to optimize a classic image processing algorithm, SOBO filter. Starting from a naive implementation widely available from web to a hardware-optimized system running at 60 frames per second at 1080p HD resolution. Let's start with a simple software that consists of reading a live video input from HDMI, apply color conversion, apply SOBO filter, convert the color space back to RGB, and output to HDMI. In this example, we will simply use a naive C implementation of SOBO filter widely available on the web. Just as a quick review, the algorithm iterates over 2 million pixels found in a 1080p HD frame and apply 3x3 matrix operations on the 9 surrounding pixels. Finally, the processed output pixel is written out to the output frame. Let's see how SDSoC can simply implement this pure C application on the Xilinx Zynq SoC. We first select functions of interest to the FPGA by simply selecting RGB to YC, SOBO, and YC to RGB. Then run the rapid estimation by clicking the build button with SD estimate configuration. After a few minutes, the performance and area estimates are presented showing very poor performance around 0.1 frames per second. Nonetheless, we can build the working Zynq system by hitting the build button again with SD release configuration. After some time, the entire SD card image with both hardware and software binaries were generated and can be run on the target board. Here's a design actually running on Zinc 702 development kit with a HDMI FMC card. As expected, the processed image is refreshed almost every 10 seconds. However, this shows how easily you were able to get a complex Zynq design with 3 hardware functions using C only. Now, you can focus on optimizing the SOBO filter to improve the overall performance. Let's go back to our naive SOBO filter code and see what is causing such a slow runtime. It turns out that it's caused by the 9 non-sequential DDR memory access executed by every pixel. This simple animation illustrates how many pixels are read in a non-sequential and overlapped fashion. With 1080p HD image consisting of 2 million pixels, we read almost 18 million pixels, which is 9 times the original image. Now, let's see how this can be optimized for hardware by using shifting line buffer and a shifting 3x3 window. With this technique, you stream in the input video pixel at a time and shift the buffer until enough data is buffered so you can apply a 3x3 filter on it. This way, you only read each pixel only once and in a sequential order, resulting in extremely efficient hardware implementation. The end result is exactly 2 million pixel reads, which is 9 times memory bandwidth saving. To apply this on your C code, it takes about 5 lines of code addition using 2 convenience types called AP line buffer and AP window. By implementing the line buffer and the window algorithms, you can simply replace the memory access to the buffer access. Now let's run estimation again with the exactly same SDSoC project. This time, the estimation result shows nearly 9 times speed up as expected. Rebuilding the project with SD release gives you the new SD card image, and you can verify the improvement on the live video stream. We're getting close. What else is a problem? Turns out each loop iteration is still being run one after another in a sequential way. As a simple illustration, if each loop iteration takes 60 cycles, we need to run it 2 million times for each frame, resulting in 124 million cycles. This is where the beauty of the hardware acceleration comes in, pipeline. You can kick off an iteration of loop every clock without waiting for the previous iteration to complete. In this case, this will theoretically result in 60 times speed up. To apply this on your C code, it's very easy. Just add a pragma called pipeline II equals 1, where II stands for initiation interval for kicking off the next loop iteration. Let's run the estimation again on the same project, and you see almost 60 times speed up as expected. Finally, running on the real hardware, the result speaks for itself. I've shown you how easily SDSoC can generate a working image processing system operating on a live video stream. By generating all the hardware connections, as well as software VSPs, a user can focus solely on optimizing algorithms. With a full understanding of the few techniques needed to optimize an image processing algorithm, you can easily get orders of magnitude speed up by changing only a few lines of C code. For more information, please visit xilinx.com/SDSoC. Thank you.